So in this one, we can practice some of the more fancy schmancy stuff I've shown you with waves a little bit, and nothing too crazy, but practice some of the other types of waves relationships we've looked at with sound and light. Now, the first one here, of course, is speed of sound, and we looked at how the speed of sound changes, and of course, speed of sound is the 331.5 plus 0.6 times temperature. It changes with a linear relationship. So basic speed of sound expression, you should be able to find out how fast the sound is, relatively simple. All right, next is a Doppler shift type question. We got a couple people. What frequency do each of the people hear from the fire truck? Okay, well, first thing I notice is the truck is moving at 15. This person is at rest. So when I use the frequency expression, first of all, the truck is moving away from them. So the frequency should get lower. So I'd want to subtract inside the bracket expression that I've shown you. The initial frequency is 5800, so that's fine. But I'd want to subtract because they are going further away. And the V that I would want to use is just the 15 because the guy isn't going anywhere. But on the other hand, on the right-hand side, the truck is going 15, the guy in fire is going 4. He's running away from the truck, but still the truck is faster. So they're actually getting closer together. So since they are actually getting closer together, I'd want to add the fraction inside the brackets, not subtract. So I'm going to add for the guy who's on fire. And for the V value, I want to use the relative speed between the two. Sure, he's running at 4, but the truck is going 15. So the truck is actually getting closer with 11 meters per second. So I'd want to add for this guy, as well as use a relative speed of 14 when I calculate the frequency. So the guy behind the truck, I should expect to get a frequency lower than 5800. And for the guy in front of the truck, I should expect to get a frequency higher than 5800. All right, next we got the lifeguard blowing his whistle. You're 84 meters away. Takes 0.238 seconds for you to hear it. What temperature is it? Okay, well, you've got a distance and a time, so you can calculate the speed of sound using basic DTV. And then once you got that, you can put that back into the temperature expression that we've shown you before and calculate the temperature of the air. Right, you got two distances from two sound sources giving a 400 hertz sound waves. What's the sound quality at your location? So this is the old S1 minus S2 divided by lambda expression we looked at to see how many waves fit in the distance differences from the points. So you might want to find the wavelength of those sound waves. You know the speed of sound. Just use the 340, get the wavelength, see how many wavelengths further away one is compared to the other. Remember, you got to be careful. Is it integer? Is it integer and a half? Is it somewhere in between? And hopefully you can figure out approximately how good the sound quality would be at your location. All right, next we got some light going on. How far apart are the bright spots? Okay, well, this is like a Young experiment type thing. Of course, lambda dy over L is the Young experiment expression. If you're looking for how far away the bright spots are, you're looking for the y value. You've got the lambda, you've got the d value, you get the length. Basically, you just got to solve for the y value. And then we're looking for the angle to the fourth minimum. So be careful because the fourth minimum would have a fringe number of 3 because it does start counting at 0. And you can either make a right triangle or you can use the sine theta expression that we've looked at before. Either way, it doesn't make any difference how you do it. You can count the y values from the middle and use the L value in tan theta. You can use the sine theta expression. It doesn't matter. Just be careful. The fringe number is going to be 3 and not 4. Connected, more Young experiment. We're looking for a couple things here. Orange light is sent through 2 openings. So you have the D value of 54 micrometers and the L value to be the 2.8 millimeters. So what you can do is you can actually find a couple things. Point A is right in the middle, and then point B is a couple maximums over. So you've got the Y value. The distance between A and B would be 2 Y values difference. So if you can find the Y value, then you can find out how far away that is. And then you're looking for the angle to the little dot. All right, that little dot is sitting on a maximum, and it's sitting, the first maximum is right in the middle. It's sitting on a fourth maximum. So the fourth maximum would have a fringe number of 3. So you can use the sine theta or the tan theta expression, doesn't matter. in order to figure out what angle would be made to that dot. Okay, so the same type of calculations as in the previous question. Okay, there's basically the Young experiment expression as well as a sine theta or tan theta one for the angles. Same type of thing for this one. Just got to find the pieces and put them together.